So namaste to all, welcome to the session. In today's class, we are going to discuss the problems based on the chapter Mechanical Properties of Solid. So we shall see the first question is like this. So here the first question what they ask is, that is 10.1. They ask, explain why the blood pressure in humans is greater at the feet than at the brain. Atmospheric pressure at a height about 6 kilometers decreases to nearly half of its value at the sea level. Through the height of the atmosphere is more than 100 kilometers. And they ask hydrostatic pressure is a scalar quantity. Even through pressure is force derived by the area. So this is based on theoretical question, and we have to give the reason for this. So here, if you understand the theory part clearly, we can possible or easily possible to give the answer. So for 10.1, the answer is like this. So pressure of a liquid is given by the relation. We know P is equal to rho g h. And from this equation, where P is the pressure, h is the height of the liquid column, and then rho is the density of the liquid, and g is the acceleration due to gravity. So it can be interpreted that pressure is directly proportional to the height. Hence, the blood pressure in human vessel depends on height of the blood column in the body. So the height of the blood column is more at the feet than it is at the brain. Therefore, blood pressure at the feet is more than it is at the brain. So next, density of air is maximum near the sea level. Density of air decreases with increase in height from the surface. So at the height of 6 kilometers, density decreases to half of its value at the sea level. Atmospheric pressure is directly proportional to density, we know. So hence, height of 6 kilometers from the surface decreases to nearly half of its value at the sea level. So next, they ask, for that reason, so when force is applied on the liquid, pressure in the liquid is transmitted in all directions. Hence, hydrostatic pressure does not have a fixed direction, and it is a scalar quantity. So this is the reason we have to mention. And this is the answer for the question 10.1. And next we shall move to next question, that is 10.2. So this is also based on theoretical question. Explain why the angle of contact of mercury with glass is obtuse, while that of water with glass is acute. This is the first one. And next they ask, water on the clean glass surface tends to spread out, while mercury on the same surface tends to form off. First we shall see the for the first reason, that is angle of contact of mercury with glass is obtuse, while that of water with glass is acute. Why? Because the reason for first question is, so we know angle between the tangent to the liquid surface at the point of contact and the surface inside the liquid is called angle of contact. So that is shown in the diagram here. So for the first diagram, mercury on the glass is shown, and second one, water on the glass is shown. So from this diagram, SLA and SA, SLA, so those are the notation used to represent. So SLA means liquid air interface, and SA is solid air, and SL means solid liquid interface at the line of contact from the diagram. So the surface force between three medias must be equilibrium. So that is already shown in the diagram. Therefore, so cos theta is given by the formula. So that is the angle of contact theta is obtuse, means SSA is less than SLA as in case of mercury on the glass. So this angle is acute if SLA less than SLA as in case of water on the glass. So mercury molecules have a short force of attraction between themselves and weak force of attraction towards solid. Hence, they tend to form a drop. So this is the answer for the question first one. And for the next question, what they ask? So next they ask, surface tension of the liquid is independent of area of the surface. So surface tension of liquid is independent of the area of the surface. Why? Because the reason is so this is the reason for the second one. So that is mercury molecules have a strong force of attraction between themselves and weak force of attraction towards solid. Hence they tend to form a drop. So here for that, for second question, water molecules make acute angle with the glass. They have a weak force of attraction between themselves and strong force of attraction towards solid. Hence they tend to spread out. And for next, what they ask the question is, so here next question, they asked, water with a detergent dissolved in it should have a small angle of contact. So here for second one, answer is this one, that is for second one. Second question, what they asked, water on the clean glass tends to spread out while mercury on the surface tends to form a drop. Why? Because, so that is for the second question, this is the answer. And third one, what they asked, water with a detergent dissolved in it should have a small angle of contact, because water with detergent dissolved in it has a small angle of contact. This is because for small angle theta, there is a fast capillary rise of the detergent in the cloth. The capillary rise of a liquid is directly proportional to the cosine of the angle of contact. So if theta is small, then cos theta will be large and rise of detergent water in the cloth will be fast. And next question. So what they ask, a drop of liquid under no external forces is always spherical in shape. So here, next for that question, the answer is like this. So a liquid tends to acquire the minimum surface area because of presence of surface tension. Surface area of the sphere is minimum for a given volume. Hence, under no external force, liquid drop always take a spherical shape. So this is the reason. And 10.3, next one. So for that, so that is also based on theoretical concept. So that one, read the question and try to answer for 10.3 yourself. Try to check it, and for 10.3 the answer is like this. And this is also based on theoretical concept. Please go through it and try to solve that one. Next, we shall see 10.4. So 10.4, so explain why to keep a piece of paper horizontal, you should blow over, not under it. When we try to close a water tap with our fingers, fast jets of water rush through the opening between the fingers. Next, the size of needle of a spray syringe controls flow rate better than the thumb pressure exerted by the doctor while administering an injection. Next, a fluid flowing out of small hole in the vessel results in the backward thrust on the vessel. Spinning cricket ball in air does not flow a parabolic trajectory. So like this they ask, these are all based on theoretical questions, and for these questions try to answer yourself and check whether these answers you are getting or not. So here these are the solutions for 10.4 based on theoretical concept only. And these are the reasons for 10.4. And go through it. And next, we shall see next problem, that is 10.5. So here, what the question is 10.5. So 10.5 is a 50 kg girl wearing high heel shoe balances on a single heel. Heel is circular with a diameter of 1 centimeter. What is the pressure exerted by the heel on the horizontal floor? So like this they ask the question. So for 10.5, so first we should try to understand what are the given things, and next from the question try to write the given things. For 10.5, so what they have given? So they have given mass, they have given, that is m is equal to 50 kg, diameter is equal to 1 centimeter they have given, that is converted into meter. So radius of the heel is got by making or dividing the diameter by 2, then we are getting 0.05 meter. And next, the area of the heel is calculated by using formula pi r square. So pi is kept as it is, or you can substitute 3.142, and radius value we substituted as 0.005. R square is there, you can square that one. And here you can do like this also, 3.142 into 0.005 whole square. You can do like this, and final answer area we got, area is equal to 7.85 into 10 to the power of minus 5 meter square. So only we got area. So by using area, we can possible to calculate force exerted by the heel on the floor. So that is calculated by using force is equal to m into g. So mass is substituted as 50 and g is substituted as 9.8. And force, if you after simplification, force we got that one as F is equal to 490 Newton. So we calculated area and we calculated force. And by using this one, next we have to calculate the pressure. So how we are going to calculate the pressure is, so we calculated force, and pressure exerted by the heel on the floor is calculated by using formula. So we already know that is Pressure exerted by the heel on the floor is given by the formula P is equal to force by area. And here force value is 490, that is substituted, and area is substituted as 7.85 into 10 to the power of minus 5. And after simplification, the pressure we got is 6.24 into 10 to the power of 6 Newton per meter square. Therefore, pressure exerted by the heel on the horizontal floor we got is 6.24 into 10 to the power of 6 Newton per meter square. So I hope you got this one. First we calculated area and we calculated force, and by using force we got that is 490 and area we got that is 7.85 into 10 to the power of minus 5. By using that, pressure is calculated by using force by area, then we got that one as 6.24. So this is the solution for 10.5. So next, so let us move to 10.6. 10.6, what they ask the question is, Torricel's barometer used mercury, Pascal duplicated is using French wine of density 984 kg per meter cube. Determine the height of the wine column for normal atmospheric pressure. So what they asked, 10.6, this one. So 10.6. So how we are going to calculate this one? First, try to write the given thing. So what they have given is, so they have given density of mercury they have given. So how much? Density of mercury, ρ1 we consider. So density of mercury, ρ1 is equal to 13.6 into 10 to the power of 3 kg per meter cube, and height of the mercury column H1 is equal to 0.76 meters, and density of French wine, let us we consider ρ2 is equal to 984 kg per meter cube, and height of the French wine column we took that one as H2, we have to find that one. So we have to find this one. So acceleration due to gravity is constant. The pressure in both the column is equal. Therefore, pressure in mercury column is equal to pressure in French wine column. According to mathematical formula, it is written as ρ1 H1G is equal to ρ2 H2G. ρ1 H1G is equal to ρ2 H2G. So in both the G is same term. So we are having ρ1 H1 is equal to ρ2 H2 from this formula. So what we have to find H2. Therefore H2 is equal to ρ1 H1 divided by ρ2. So substitute the given values. So here from we modified that formula, and after substituting what we are getting, so here we got, so H2 is equal to, so H2 is equal to ρ1 H1 divided by ρ2 it is, and H2 we have to calculate. So ρ1 we substituted that one as 13.6 into 10 to the power of 3, and H1 is substituted as 0.76, and ρ2 is substituted as, so what we substituted, 984 what they have given, and after substituting, and we got the height H2 as 10.5 meters. Therefore, height of the French wine column for normal atmospheric pressure is 10.5 meters. So this is the solution for 10.6. So next we shall see 10.7. So what they asked, A vertical horseshoe structure is built to withstand maximum stress of 10 to the power of 9 Pascal. Is the structure suitable for putting up on the top of an oil well in the ocean? Take the depth of ocean be roughly 3 kilometers. Ignore the ocean current. Like that, they ask the question. So for 10.7, let us see how to solve that one. So from the question, what they have given. So from the question, they have given that is so maximum allowable stress for the structure. Let us consider pressure is equal to 10 to the power of 9 Pascal. In the question itself, they have given, and depth of ocean D, they have given 3 kilometer, and that is converted in terms of meter, then it becomes 3 into 10 to the power of 3 meters. So density of the water, that is always constant, rho is equal to 10 to the power of 3 kg per meter cube, and acceleration due to gravity is always constant, that is 9.8. Pressure exerted because of sea water at depth D is given by the formula D is equal to rho D into J, and density rho is 10 to the power of 3, and depth D they have given in the question itself, that is 3 into 10 to the power of 3, and G value is constant, that is 9.8. We substituted here, and after substituting, the value of D we got is 2.94 into 10 to the power of 7 Pascal. So maximum allowable stress for the structure 10 to the power of 9 Pascal is greater than the pressure of the sea water, because sea water 2.94 into 10 to the power of 7 Pascal is that value. Pressure exerted by the ocean is less than the pressure exerted that of structure can withstand. Hence, structure is suitable for putting up on the top of an oil well in the ocean. So like this, we have to give the reason. Next question, that is 10.8. A hydraulic automobile lift is designed to lift cars with a maximum mass of 3000 kg. The area of cross section of the piston carries load is 425 centimeters square. What maximum pressure would the smaller piston have to bear? So this is the question, that is 10.8. So let us see how to solve this one. So from the question, what they have given is so from the question, first read the question once, twice or thrice, and what they have given. So from the question they have given is maximum mass of car that can be lifted M is equal to 3000 kg in the question itself they have given, and area they have given 425 centimeters square, and that is converted in terms of meter it is. And that maximum force exerted by the load can be calculated by using formula F is equal to M into G, and mass they have given, that is 3000, and G value is 9.8. By using that force we got is 29,400 Newton. So, and the pressure is calculated by using formula P is equal to force by area, and force we got is, so that is 29,400 divided by area, how much we got? So that is 425 into 10 to the power of -4. So if you simplify this one, so we are getting pressure. So here I showed here. That is, pressure we got is, so how much we are getting? So the pressure we got is 29,400 divided by 425 into 10 to the power of minus 4. If we calculated, that is pressure we got is 6.917 into 10 to the power of 5 Pascal. Therefore, pressure is transmitted equally in all directions in a liquid. Therefore, maximum pressure that the smaller piston would have here is 6.17 into 10 to the power of 5 Pascal. So, this is the solution for 10.8. Next, we shall move to 10.9. So, what they ask 10.9? A U-tube contains water and methyl spirit separated by mercury. Mercury column in 2 arms are in level with 10 centimeter of water in one arm and 12.5 centimeter of spirit in the another. What is the specific gravity of the spiritum to kg? So how to solve that one? So for that diagram, first we need to assume one diagram. So that is, so first we have to assume, and by assuming that one, we are drawing this one. So here in the U-tube, so in the question, from the question, so by assuming we need to draw this diagram. So the given system of water, mercury and methyl spirit, so that is drawn in the diagram. So in this diagram, what are the given things from the question is, so this is the spirit. So height of the spirit is 12.5 centimeter. This is spirit. And next, water level they have mentioned, that is, so this is the water, that is 10 centimeter, and remaining thing with all is mercury. So that is shown here. And this is A point, B point, C point and D point. That represents the levels. And this P0 is the pressure in the tube. In one tube, spirit is taken, in one tube, water is taken, and at the bottom of the U-tube, mercury is present. So from the question, height of the column they have given 12.5 centimeter and H2 is 10 centimeter. So this is H1 and this is H2 for spirit. H represents height. So from this, so we wrote the given things. P0 is the atmospheric pressure, ρ1 and ρ2 are the density of spirit and water. And next, pressure at B is given by the formula P0 plus of H1 ρ1 into G. Pressure at point D is given by P0 plus of H2 ρ2 into G. So we need to calculate pressure at point B and D is same, is we are equating that one. And from the formula, from that formula, so just we need to find the specific gravity. So pressure at point B and D is same. Therefore, it is written as P0 plus of rho H1 ρ1 G is equal to H2 ρ2 G plus of. So here P0 pressure, that is same, plus of P0 at both ends, that is same. So from this we need to find specific gravity. So that is Gg is same, get cancel, remaining. So this we got ρ1 by ρ2 is equal to H2 divided by H1. And we need to find this one. And H2 they have given, that is 10. H1 is 12.5. And after simplification, we got specific gravity is 0.8. So, got this one? Okay, well, next we shall move to next question. So, next question what they asked, question number 10.10. So in the problem 10.9, 15 centimeter of water and spirit each are further poured into respective arms of the tube. What is the difference in the levels of mercury in 2 arms? Specific gravity of mercury is 13.6. Means in order to solve this problem, we have to again draw the diagram of before problem, that is 10.9. So whatever the diagram we considered, same diagram we are considering not to solve 10.1. So same diagram. To this again we are adding the level of the spirit and the water column. How much? 15 centimeters. Same diagram. For this we are adding 15 centimeters level of spirit and water we are adding. So by using the given data from the 10.9 problem, so same thing, same diagram, assume that one. So height of the water is actually how much they have given. So height of the water they have given H1 initially in that diagram 10 centimeter they have given. But we need to add 15 centimeter because in the question they have given, we are adding. So H1, if we add this one, we are getting sum of these to 25 centimeters. And height of the spirit column is H2 we considered. And that is 12.5 plus of 15, we got 27.5 centimeters. Density of water we consider rho 1 and density of spirit we consider rho 2. So those are given in the question itself. Density of mercury is always constant, that is 13.6 grams per centimeter cube. So let H be the difference between levels of mercury and the two arms. Therefore, pressure exerted by height of mercury column is given by the formula rho G H. So by using these given data, so we have to find H. Therefore, we need to find H here from the formula rho G H. So by using that one, we need to write the formula and we are taking the difference of those two. So how we are writing? So first, by using rho G H into G is acceleration due to gravity, rho is the density. So that is substituted. Let us consider this one as equation 1. And next, difference between pressure exerted by water and spirit is given by the formula H1 rho 1 G minus of H1 rho here H1 rho 1 G minus of H1 rho 1 G here. So in both the equation, G is the common term and take this one difference we are taking. So this is H2 rho 2 into G here. So G is the common term we take outside and remaining values we substituted that one. And after simplification, we got this one as 3G. So let us consider this one as equation 2. Equating equation 1 and 2. This is equation 1 and this is equation 2. So equation 1 is 13.6 G and this is equation 2. That is 3G we got. So from this we need to calculate H value. So keep H here, remaining term bring this here. So this becomes H value is equal to 3G divided by 13.6 G. G gets cancelled, 3 divided by 13.6. We are getting that one as 0.2205. That is almost equal to 0.221 centimeter. So therefore, hence the difference between levels of mercury in two arms we got is 0.221 centimeter. So got this one? Okay, well, next we shall move to next question, that is 10.11. So that is based on theoretical question. Go through it and try to understand that one. So can Bernoulli's equation be used to describe flow of water through a rapid in a river? Explain they ask. So the reason is, so according to Bernoulli's equation, cannot be used to describe the flow of water through rapid in a river because of turbulent flow of water. So this principle can only applicable for the streamline flow that we already discussed. So if you understand the theory concept clearly, it can be easily possible to understand. So next one, 10.12. So 10.12 also based on theoretical question. So go through it, try to understand the reason. 10.12. So for 10.12, the reason is it does not matter if one uses Gauss pressure instead of active pressure while applying Bernoulli's equation. 2 points where Bernoulli's equation is applied should have significantly different atmospheric pressure. And next question, 10.13. Go through the question. And here for 10.13, so what they asked, 10.13, the question is like this. Glycerin flows steadily through a horizontal tube of 1.5 meter and radius 1 centimeter. If amount of glycerin collected per second at one end is 4 into 10 to the power of minus 3 kg per second, what is the pressure difference between two ends of the tube? So, and density of glycerin they have given, viscosity of glycerin they have given, that is 0.83. And here, by using this given data, first try to understand the question and then write the given things from the question. So for 10.13, so what are the given things? So they have given length of the tube they have given. So how much they have given? Length is 1.5 meter. How much they have given? Length is 1.5 meter. And radius of the tube they have given 1 centimeter. And that is converted into meter, that is 0.01 meter. Diameter of the tube is nothing but 2 times of radius. So they have given 0.02 meter. Glycerin is flowing at the rate of 4 into 10 to the power of minus 3 kg per second. Mass they have given 4 into 10 to the power of minus 3 kg per second. Density of glycerin rho is equal to 1.3 into 10 to the power of 3 kg per meter cube. Viscosity of the glycerin is represented by meter is equal to 0.83 Pascal second. And volume of the glycerin flowing per second is calculated by using formula V is equal to mass by density of the glycerin. And these are the given data. And by using these given data, so let us calculate first volume. So volume is, if we calculate by substituting mass and density, volume we got is, so that is 3 into 3.08 into 10 to the power of minus 6 meter cube per second. Next, by using that one, according to Poiseuille formula, so we know how we are going to write. This is one new formula you are having. According to Poiseuille formula, we are writing this one. Pi rho r raised to 4 divided by 8 beta into L. It is the pressure difference between two ends of the tube. And from this formula, the pressure formula we got, just modify that one. E is equal to, just make the cross multiplication, V8 beta L divided by pi r raised to 4. And V value is substituted as 0.38 and 8 is kept constant. So 8 is kept constant and this is the value of meter and this is the value of L, and this pi value is constant and this is the value of R. And after substituting, we got the value is 9.8 into 10 to the power of 2 Pascal. So next, by using this one, Reynolds number. So why we are using that one? In order to identify the type of flow of liquid, we are using that one. So we know Reynolds number is given by the relation R is equal to 4 rho V. R is equal to 4 rho V divided by pi d beta we are using. So 4 is kept as it is. So this is the value of rho and this is the value of V. This 4 is kept as it is. Pi is constant. That is V value is 0.02 and beta value is 0.83. By substituting, we got R value as 0.3. And by this formula, we are possible to identify the type of flow of liquid. So that is, it is laminar flow of liquid. So next, we shall move to 10.14. So what is the question? In a test experiment, a model aeroplane in a wind tunnel, the flow speed of upper and lower surface of wing are 70 meters per second and 63 meters per second. What is the lift on the wing? If its area is 2.5 meters square, density of air to be 1.5 kg per meter cube R. So what is the lift on the wing? Anta kelidare. So how to solve this one? 10.14. For 10.14, first read the question and try to write the given thing. So speed of the wing that we considered V1 is equal to 70 meter per second and V2 is equal to 63 meter per second and area is 2.5 meter square. Density of air is 1.3 kg per meter cube. So according to Bernoulli's principle, we have the relation P1 plus of half rho V1 square is equal to P2 plus of half rho V2 square. So from this formula, so we know, so this is the relation we wrote according to Bernoulli's theorem. So we want pressure difference P2 minus of P1 is equal to 1 by 2 rho V2 V1 square minus of V2 square. From this equation, P1 and P2 are the pressure on upper surface of the wing and lower surface of the wing. And we need to calculate pressure difference between upper and lower surface of the wing. So that provides the lift. So just how to calculate that one? So here by using Bernoulli's principle, so lift of an wing is nothing but difference of pressure. So difference of pressure is given by the formula. So P2 minus of P1 into area. So that is P2 minus of P1 is from Bernoulli's principle, it is substituted as half rho V1 square minus of P2 square into area. So half is kept as it is. Density is substituted as 1.3 and here V1 value is 70. We made that one square factor and the area is 2.5. And after substituting all those, if you calculate this one, so P1 minus of P2 into area, we got that one as 1512.87. And if you shift the digit, that it become 1.51 into 10 to the power of 3 Newton. So that is the lift on the wing of the A we got. So just check whether this much of answer we will get or not. So next question is 10.15. So they have given the diagrams A, B and A and B refers to steady flow of non-viscous liquid which of two figure is right and height. This is based on theoretical concept, and the answer for this is like this. Go through it and try to understand the concept, what it is involved in it. And this is for A. And for the answer B. So here, these are the reasons. Go through it and try to understand the concept. And next we shall move to next question, that is 10.16. So what is the question? The cylindrical tube of spray pump has a cross section of 8 centimeters square. One end of which has 40 fine holes each of diameter 1 millimeter. If the liquid flows inside the tube is 1.5 meter per minute, what is the speed of the ejection of the liquid through the hole? They ask the question. And from the question, we need to write the given data. So first what they have given. So from the question, area of cross section A1 is equal to 8 centimeters square, and we converted in terms of meter. Number of holes is 40. So diameter of the hole they have given 1 millimeter, and that is converted in terms of meter. So read the question, and after understanding, we are possible to write the given data. So diameter they have given, that is converted into meter, and radius from diameter we got 0.5 into 10 to the power of minus meter. Area of cross section is calculated by using formula pi r square. This is pi and this is r value. And total number of area for 40 holes we need to calculate. Formula we are using is area. A2 is equal to n number of holes into area. So this is n number of holes, n is 40, pi value is constant, and area is substituted, value is 0.5. And after calculating, we got that one 31.41. And next, speed of flow of liquid inside the tube V1, it is given 1.5 meters per minute. So if you convert in meter per second, we got 0.025. And speed of ejection of the liquid through the hole V2, we need to calculate here. Let us consider V2. And here, we need to calculate V2 here. So according to equation of continuity, we know the formula. So that is A1 V1 is equal to A2 V2. From this we got V2 is equal to A1 V1 divided by A2. So here substitute the values. A1 is 8 into 10 to the power of minus 4 and V1 is 0.025 and A2 value is, so that is substituted as 31.31, and after that we got V2 value is 0.633 meters per second. Therefore, speed of ejection of the liquid through the hole we got is 0.633 meters per second. So shall we move to next? So next question is like this, 10.17. A U-shaped wire is dipped in a soap solution and removed. The thin soap film formed between wire and light slider supports a weight of 1.5 into 10 to the power of minus 2 Newton. So the length of the slider is 30 centimeter. What is the surface tension of the film? They ask the question. So read the question, try to write the given things, and the given things what they have given is, so they have given from the question, weight of the soap solution W is equal to 1.5 into 10 to the power of minus 2, length of the solder L is equal to 30 centimeter and that is converted in terms of meter, that is 0.3 meter, and total length of soap solution, it has two free surface, therefore it is written as total length is equal to 2 times of L. So this is 2 and length value is substituted as 0.3 and we got 0.6 meter it is. And next, surface tension is calculated by using formula weight divided by 2L. And here this is the weight and this is the total length we got is 2L value, this one. So after substituting, we got surface tension 2.5 into 10 to the power of minus 2 Newton per meter. So I hope you got this one. Okay, we shall see next one. That is 10.18. So three figures they have given. So 10.18 shows a thin liquid film supporting a small weight 4.5 into 10 to the power of minus 2 Newton. What is the weight supported by a film of same liquid at the same temperature? In the figure B and C, explain the answer physically. Like that they ask the question. So here, see the diagram first. And in case A, means that is which one? So in case A. So for this case, so here, what is the reason? So length of the liquid film supported by the weight. So here length they have given L is equal to 40 centimeters they have given. If you converted into centimeter, that it becomes 0.4. And weight they have given that is 4.5 into 10 to the power of minus 2 Newton they have given. And liquid surface, it has a two free surface. Therefore, surface tension is calculated by using formula W divided by 2L. Therefore, we got that one as 4.5 into 10 to the power of minus 2 whole divided by 2 into 0.4. If you simplify this one, surface tension we got is 5.625 Newton per meter we got. So just if you observe B and C in these two cases, so or if you observe all the figures, liquid is the same, temperature in all also same. So hence surface tension in figure B and C is also same because that is surface tension here also same we are getting, that is 5.625 Newton per meter. Since length of the film in all the cases is 40 centimeters, so length they have given. Since length is same in all the cases, therefore weight supported in each cases is same, that is 4.5 into 10 to the power of minus 2 Newton. So what they have given, so that is same. So this is the reason. So next we shall see next one. That is 10.19 we shall see. So what they have given the question is for 10.19. So what is the pressure inside the drop of mercury of radius 3 millimeter at room temperature? Surface tension of mercury at that temperature is 4.65 into 10 to the power of minus 1 Newton per meter. Atmospheric pressure is 1.01 into 10 to the power of 5 Pascal. So also give the excess pressure inside the drop they have given. So from the question, so they have given radius of the mercury drop R is equal to 3 millimeter and surface tension they have given 4.65 into 10 to the power of minus 1 Newton per meter. Let us consider atmospheric pressure be P0 And total pressure inside the mercury drop, that is calculated by using formula excess pressure inside the mercury plus of atmospheric pressure. So by calculating like that, so we got the excess pressure inside mercury plus of atmospheric pressure. So inside the mercury, that is given by 2s divided by r. P naught is the atmospheric value, that is substituted as 1.01, and this is 2 is constant, and this is the value of s, and this is the value of r. And total pressure inside the mercury drop we got is 1.01 into 10 to the power of 5 Pascal. So initially we got this much of value, and excess pressure is calculated by using formula 2s divided by r. So whatever 2s, so this one 2 into s value is 4.65 into 10 to the power of minus 1 divided by r. So if you simplify this one, so how much we are getting? So only that is excess pressure we need to calculate. So excess pressure we got is, so what is the excess pressure? So excess pressure we got is 310 Pascal. So that is very easy. So next we shall see next one, that is 10.20. So what is the question? So what is the excess pressure inside a bubble of soap solution of radius 5 millimeter? Given surface tension of soap solution at temperature 20 degrees centigrade is 2.50 into 10 to the power of minus 2 Newton per meter. If an air bubble of same dimension were formed at depth of 40 centimeter inside a container containing the soap solution, what would be the pressure inside the bubble and the question ಕೇಳಿದ್ದಾರೆ. So how to calculate this one? Read the question, try to understand that one. So from the question, what they have given, excess pressure of the soap bubble is 20 Pascal. Pressure inside the bubble is 1.06 into 10 to the power of 5 Pascal. And soap bubble of radius is 5 millimeter, that is converted in terms of meter. And surface tension of soap solution they have given, S is equal to surface tension, sometimes it is represented as S, or you can use the letter T. So 2.50 into 10 to the power of minus 2 Newton per meter they have given. And from that, relative density of soap solution is 1.20. Density of the solution rho is equal to 1.2 into 10 to the power of 3 kg per meter cube. Air bubble formed at the depth h is equal to 40 centimeter, and that is converted into meter, that is 0.4 meter. And radius of the air bubble is 5 millimeter, and if you convert in terms of meter, that becomes 5 into 10 to the power of minus 3, and 1 atmospheric value is always constant, that is 1.01 into 10 to the power of 5 Pascal. Acceleration due to gravity is constant, therefore excess pressure inside the soap bubble is given by the relation, so P is equal to 4S divided by R, and 4 is kept as it is. Surface tension is 2.5 into 10 to the power of minus 2, and radius value is 5 into 10 to the power of minus 3. After substituting all those, so we got a 20 Pascal as a pressure, excess pressure. Therefore, we need to calculate excess pressure inside the soap bubble is 20 Pascal. So we got that one. So excess pressure inside the air bubble is given by the relation P dash, we consider that one. So P dash is equal to 2F divided by R. So value of surface tension and radius is substituted, and we got that is 10 Pascal. Therefore, excess pressure inside the air bubble is 10 Pascal. So at a depth of 0.4 meter, total pressure inside the bubble is given by the formula atmospheric pressure plus of rho GH plus of P dash. So substitute all those values, and after substituting, so we getting that one as, so atmospheric pressure plus of rho GH plus of P dash. P dash we got is 10, and here atmospheric pressure value is 1.01, and H value is, so G value is 9.8, rho value is 1.2 into 10 to the power of 3, and H value is 0.4. By substituting all those, we got So the value is 1.06 into 10 to the power of 5 Pascal. So got this one? Okay, well. So next, we shall move to next problem. So that is 10.21. A tank with a square base of area 1 meter square is divided by a vertical portion in the middle. The bottom of the portion has small hinged door of area 20 centimeter square. Tank is filled with water in one component and acid in another, both of height 4 meter. Compute the force necessary to keep the door closed anta kelidara. So from the 10.121, so what they have given base area of the tank A is 1 meter square and small letter A area of the hinged door is 20 into 10 to the power of minus 4 meter square. Density of water rho 1 they have given 10 to the power of 3 kg per meter cube. Rho 2 they have given 1.7 into 10 to the power of 3 kg per meter cube. Height of the water column H1 they have given 4 meters and acid column height H2 is 4 meters they have given. Acceleration due to gravity is constant. By using these given data, pressure due to water is given by the formula P1 is equal to H1 rho 1 into G, and same thing due to acid is P2 is equal to H2 rho 2 into G. And here first we need to calculate pressure P1. So that is calculated by using formula. We already know that one. P1 is equal to that is H1 rho 1 into G. So H1 value, so after that one, substituting all those, so we got P1 value as 3.92 and pressure due to acid that is calculated by using formula H2 rho 2 into G, and substituting all those values P2 we got 6.664 into 10 to the power of 4 Pascal. And P1 we got and P2 we got, and next we need to take the pressure difference. So if you take the pressure difference of these two, so what we are getting? So pressure difference between water and acid column. So that is given by the formula. So that is pressure difference between water and acid column is given by delta P is equal to P2 minus of P1. So P2 is substituted as 6.664 into 10 to the power of minus 4 and P1 is substituted as 3.92. So difference of pressure we got 2.744 into 10 to the power of 4 Pascal. So here hence force exerted on the door is delta P into area. So change in pressure, so this is delta P we got and the area we got is 20 into 10 to the power of minus 4. So after simplification, so this one, so this is 2.744 into 10 to the power of 4 it is, and area is 20 into 10 to the power of minus 4. So after simplification, we got this one as 54.88 Newton. Therefore, force necessary to keep the door closed is 54.88 Newton. So this is the solution. So next we shall see 10.22. So what they ask the question is, a manometer reads the pressure of a gas in an enclosed as shown in the figure. They have given the diagram. When a pump removes some of the gas, the manometer reads as in the figure 10.25b. So two diagrams they have given. First one is A, second one is B. So the liquid, two diagrams they have given, and here in B case, the liquid used in the manometer is mercury and atmospheric pressure is 76 centimeter of mercury. So give the absolute and Gauge pressure of the gas in the enclosure for case A and B in units of centimeter of mercury anta kelidara. So how would the levels change in case of B? that is 13.6 centimeter of water are poured in the right left of the manometer anta kelidara. So here see the diagram, and from the figure 1 or from this figure A and B two diagrams they have given, and from these two diagrams, so what they have given, so from the figure A, atmospheric pressure P naught they have given, that is 76 centimeter of Hg. Difference between levels of mercury they have given, that is difference of pressure is nothing but Gauge pressure, that is 20 centimeter, and absolute pressure is calculated by using the formula atmospheric pressure plus of Gauge pressure. We got 96 centimeter. And from the diagram B, so difference between levels of mercury they have given, that is difference of pressure is nothing but Gauge pressure minus 18 centimeter of Hg, and absolute pressure is calculated by taking the sum of atmospheric pressure and Gauge pressure. We got 58 centimeter. And 13.6 centimeter of water is poured in the right limb of the figure B. So therefore, relative density of mercury is 13.6. Hence, so H is the difference between level of mercury in two limbs. Therefore, pressure in right limb is given by the formula atmospheric pressure of 1 centimeter of Hg. So by using that one, let's just consider that one as equation 1. And hence pressure in the left limb is given by PL on the left, pressure in the left limb, that is 58 plus of height. Let us consider as equation 2. So equating equation 1 and 2. So the height, how much we are getting? So the height we are getting just by equating equation 1 and 2. So we got that one height, that value is 19 centimeters. Just we equated this equation 1 and equation 2. So equation 1 is 77, that is equation 1, and this is equation 2. From this we calculated H value. So H value how we are calculated? So 77 minus of 58, we are getting that one as, so that is 19 centimeter is the difference. So, well, we shall move to next question, that is 10.23. So that is based on theoretical concepts. So go through it. For 10.23, the solution or reason is like this. And next 10.24 we shall see. So 10.24. So what they ask, so during blood transfusion, so 10.24, so what they ask is during blood transfusion, the needle is inserted in a vein where Gauge pressure is 2000 Pascal. What height must the blood container be placed so that blood may just enter the veins? So from the question, pressure they have given 2000 Pascal, density of blood rho is equal to 1.06, exhalation due to gravity they have given, and we need to calculate H value we have to find. We know pressure of the blood container is given by the formula P is equal to rho, that is rho G H, and we need to calculate H value. So therefore H is equal to P divided by rho into G. And here pressure they have given, that is 2000 divided by density is 1.06 into 10 to the power of 3 into G value they have given 9.8. So if you simplify this one, we are getting 0.1925 meter. That is the value of height we got. Therefore, blood may enter the veins if the blood container is kept at the height greater than the 0.1925 meter. It is about almost equal to 0.2 meter. You can consider. So, okay, next we shall move to next question, that is 10.25. So what is the question? 10.25 in deriving Bernoulli's equation, we equated the work done on the fluid in the tube to its change in the potential kinetic and kinetic energy. What is the largest average velocity of the blood flow in the artery of diameter 2 into 10 to the power of minus 3 meters? If the flow mass remains laminar, so these one they are, do the dissipative force become more important as the fluid velocity increases? Discuss qualitatively ಅಂತ question ಕೇಳಿದಾರ. So for this, so what they have given, diameter they have given. So how much diameter they have given? So diameter they have given is, diameter of the artery D is equal to 2 into 10 to the power of minus 3. Viscosity of the blood neta is equal to 2.084. Density of the blood rho is equal to 1.06 into 10 to the power of 3 kg per meter cube. And Reynolds number NR is equal to 2000. Therefore, large average velocity of the blood is given by the formula. So average AVG and the average velocity of the blood is given by the formula Reynolds number into neta divided by rho into D. So NR value under Reynolds number they have given 2000 into neta 2.084 into 10 to the power of minus 3 divided by rho value is 1.06 into 10 to the power of 3 it is, and D value is 2 into 10 to the power of minus 3. So after calculating average value, we are getting 1.66 meter per second. So this is the value. So as the fluid velocity increases, dissipative force become more important. So because rise of turbulence, that is the reason for this one. Turbulence flow causes the dissipative loss in the fluid. So I hope you got this one. So next we shall see 10.26. So 10.26, what is the question? What is the largest average velocity of the blood flow in an artery of radius 2 into 10 to the power of minus 3 meters? If a flow mass remains laminar, what is the corresponding flow rate anta kelidara? So from 10.26, from the question they have given diameter of the artery they have given, so that is 2 into 10 to the power of minus 3, that is 4 into 10 to the power of minus 3 they have given. So what they have given, so that is diameter they have given. So diameter how much they have given? So diameter is 4 into 10 to the power of minus 3. So that is diameter of the artery. So viscosity of the blood value they have given. Viscosity of the blood. So how much it is? So here 10.26, no, this one. So okay, well, so from that diameter they have given, viscosity of the blood they have given, density of the blood is rho value they have given 1.06 and Reynolds number 2000, and average velocity of blood is given by the formula average velocity is equal to NR meter divided by rho into D. And after calculating same steps we are following as we calculated before, that we got 0.983 meter per second. Therefore, so here flow rate, average velocity we got 0.983 meter per second. Flow rate is given by the relation R is equal to, so which relation we are using? So R is equal to pi r square into average velocity. Pi value is constant, that is 3.142. Radius value is 2 into 10 to the power of minus 3 whole square. And average velocity we got is, so average velocity we got is 0.983. And therefore, After simplification, R value we got that is 1.235 into 10 to the power of minus 5 meter cube per second square, per second it is. So that is the corresponding flow rate we got. And next we shall see 10.27. So what is the question? 10.27. So the question is like this. A plane is in level flight at constant speed and each of its two wings has area of 25 meters square. If the speed of air is 180 kilometers per hour over the lower wing and 234 kg per hour over the upper wing surface, determine the plane mass ಅಂತ ಕೇಳಿದಾರ. So read the question, try to understand that one, and from the question what they have given. So area of the wing A is equal to 2 into 25 we are doing, therefore 50 meters square we got. Area of air over the lower wing we consider V1 is equal to 180 kilometers per hour. So if we convert into meter per second, so we got 50 meters per second. And next same thing, so what they have given, so V1 they have given, V2 means that is speed of air over the upper wing, so that is V2, and area they have given that is converted into meter, so V2 they have given 234 kilometers per hour. If you convert into meter per second, we got 65 meters per second. Density of air is 1 kg per meter cube. Pressure over the lower wing we consider P1, and for upper wing pressure is P2. So upward force on the plane wing can be obtained by using Bernoulli's equation. So by using Bernoulli's equation, how we are writing is, so by using Bernoulli's equation, so we are writing like this. Therefore, according to Bernoulli's equation, it is written as, that is P1 plus of half rho V1 square is equal to P2 plus of half rho V2 square. So take the differences of pressure, that is P1 minus of P2 is equal to half rho V1 square minus of V2 square. Therefore, difference of pressure into area, that is nothing but upward force on the plane wing. So that is calculated by using formula this. So difference of pressure into area, area is kept as it is. Difference of pressure according to Bernoulli's principle, it is written as half rho in the bracket V2 square minus of V1 square into area. So using Bernoulli's equation or using equation 1, we written that one. So after this, what we did is just substitute the given values. So what they have given, so here half is kept as it is, and the rho value is so substituted as, so half is kept as is, the density is substituted value. So this is V1, V2 is 65 and V1 is 50, that is square factor is there. So area is substituted as 50 and we got that one as 43,125. So according to Newton's formula, so force is given by the formula F into M in, calculated by using formula force is equal to mass into acceleration due to gravity. So by using that one, so force is calculated here. So next, by using that one, mass we got is so 4,400 kg. So here, by using force formula, we calculated. So by using force formula, so here we want to calculate M, therefore F divided by G here. So here this is the value of F and this is the value of G. Therefore mass we got is 4,400.51. So that is almost equal to 44,000 kg. Therefore mass of the plane is about 4,400 kg. is. Okay, next we shall move to next one. That is 10.28. So here in Mulligan's oil drop experiment, what is the terminal speed of the unchanged drop of radius 2 into 10 to the power of minus 5 meter and density 1.2 into 10 to the power of 3 kg meter cube? Take the viscosity of air at the temperature of experiment to be 1.8 into 10 to the power of minus 5 Pascal. How much is the viscous force on the drop at that speed? Negligible buoyancy of the drop due to air anta kelidara. So which is that one? So 10.28 it is. So here 10.28. So from the question what they have given, first read the question and write the given things. So terminal speed they have given, that is 5.8. So here from the question, and viscous force is 3.9. So what they have given? So terminal speed they have given, that is 5.8 centimeter per second, and viscous force they have given. Viscous force they have given, that is 3.9 into 10 to the power of minus 10 Newton, and radius of they have given, that is 2 into 10 to the power of minus 5 meter. Density of unchanged drop, that is rho is equal to 1.2 into 10 to the power of 3 kg per meter cube, and viscosity of air neta value they have given, that is 1.8 into 10 to the power of minus 5 Pascal per second. Pascal second. So terminal velocity, that is calculated by using formula. Terminal velocity is calculated by using formula. So V is equal to 2r square into rho minus of rho naught into G divided by 9 into beta. So substitute all the given values. So that is, after substituting, so we got that one as into G value is 9.8 divided by 9 into neta value is 1.8 into 10 to the power of minus 5. So after simplification, we got 5.8 centimeter per second. And viscous force is calculated by using formula X is equal to 6 pi meter R into mu. So substitute all those values and we got 3.9 into 10 to the power of minus 10 Newton. So here, so this one, for this is the solution. So already I shown here. So viscous force value we got 3.9 into 10 to the power of minus 10 Newton. So next we shall move to next question, that is 10.29. So mercury has an angle of contact equal to 140 degrees with the soda lime glass. A narrow tube of radius 1 millimeter made of this glass is dipped through containing mercury. By what amount does the mercury dip down in the tube relative to the liquid surface outside? So surface tension of mercury at the temperature of experiment they have given, that is 0.465 into Newton per meter. Density of mercury is 13.6 into 10 to the power of 3 kg per meter cube. And here solution for this is from the given question. Angle of contact theta is equal to 140 degree and radius of the narrow tube R is equal to 1 millimeter, that is converted into meter. Surface tension of mercury is 0.465 Newton per meter. Density of mercury is 13.6 into 10 to the power of 3. Dip of height of mercury we considered as h. Acceleration due to gravity is 9.8. surface tension is related with the angle of contact that is given by the formula F is equal to rho g h into R divided by cos theta. From that H formula we got 2s cos theta divided by R rho into G, and H value we got minus 5.34. So how we got this one is, it is very easy. So some surface tension formula. So H is equal to 2s cos theta divided by R into rho G. 2 is kept as it is, cos theta is 140 degree theta value, and S value, this one 2, and this one radius and density, and this is G value, and this is R value. After substituting H value, we got minus 5.34 millimeter. So hence negative sign shows the decrease in the level of the mercury. Mercury level dips by 5.34 millimeter. So got this? So next we shall move to 10.30. Two narrow bores of diameter 3 millimeter and 6 millimeter are joined together to form U-tube open at both ends. If U-tube contains water, what is the difference in its level in the two limbs of the tube? Surface tension of water, the temperature of the experiment is 7.3 into 10 to the power of minus 2 Newton per meter, and angle of contact is 0, and density of water is 1 into 10 to the power of 3 kg per meter cube. Like that they ask the question. So from this question, so read the question and try to write the given things. So what are the given things? So from the question they have given diameter of the first bore we consider D1 is equal to 3 millimeter, and R1 radius of the first bore 1.5 into 10 to the power of minus 3, and diameter of the second bore D2 they have given, radius of second bore R2 they have given 3 into 10 to the power of minus 3, and surface tension of water is 7.3 into 10 to the power of minus 2, angle of contact is 0 for water and bore surface, density of water is 1000, acceleration due to gravity is 9.8. Let H1 and H2 be the height of the water rises, and for first and second tube. So from that H1 is equal to 2s cos theta divided by R1 into rho G. Let us consider that one as equation 1, and H2 is given as 2s cos theta divided by R2 into rho G. So difference between levels of water in two limbs of tube can be calculated by using formula. So which formula? So that is calculated as by taking the difference of these two. So here just we took the difference of those two. So if you take the difference of those two, what we are getting is, so 2s cos theta divided by rho G is common in both the terms. 2s cos theta divided by rho G is the common term. Remaining 1 by R1 minus of 1 by R2 is the remaining 1 by R2. And 2 and S value is substituted as 7.3. 1 by this is R1 and this is R2 value. And this is rho value and this is G value. And after calculating, we got 4.97 millimeters. Got this one? Last one, that is 10.31. So what they ask? So last problem. So it is known that density rho of air decreases with height. We already know. So where rho naught is 1.25 kg per meter cube, density at sea level and y naught is constant. This density varies is called law of atmosphere. Obtain this by assuming that temperature of atmosphere remains constant. Also assume the value remains constant. A large helium balloon of volume 1425 is used to lift payload of 400 kg. Assume the balloon maintains constant radius as it rises. How high does it rise? and Y naught value they have given, density of helium they have given, that is 0.18. And how to solve this one means, so first volume of balloon they have given V value 1425 meter cube, mass they have given 400 kg, acceleration due to gravity is always constant, that one, that is 9.8 meter per second square. And next, Y naught they have given in the question itself, density of helium they have given, density of balloon we consider rho, height of the column we considered y, density decreases with height, that is given by the relation rho is equal to rho naught into e raised to minus y naught. So from that relation, rho by rho naught is equal to e raised to minus y by y naught. So let us consider that one as equation 1. And density varies is called law of atmosphere. It can be informed from equation 1. Rate of decrease in density with height is directly proportional to density. So that is given by the formula minus of d rho by dy is directly proportional to rho. If we remove the directly proportionality symbol, we are introducing the equality symbol. So finally we got d rho by rho is equal to minus of k into dy, where k is constant. So height changes from 0 to y value. So by integrating this one from the limit of from lower value to higher value, so this one you are able to understand completely after when you learn the integration process. So if you integrate from lower value to higher value, so we got that one as rho by rho naught is equal to e raised to minus k into y. And comparing equation, let us consider that one as equation 2. Comparing equation 1 and 2, we got y naught is equal to 1 by k or k is equal to 1 by y naught. So from equation 1 and 3, rho is equal to rho naught e raised to minus y into y naught. So here that is for A. And for B, so how we are solving that one? So from integration method, so this one you can possible to understand clearly after learning integration process. So finally we got that one. After integrating, we got rho is equal to rho naught e raised to minus y by y naught. So for B one, so we know density is given by mass by volume. So here we are calculating mass of payload divided by plus of mass of helium divided by volume we are making. So this is written as m plus of V into rho of helium plus divided by volume. So this one 400 plus of 1425 into 0.18 divided by 1425. After simplification, we got 0.46 kg per meter cube. So from equation 2 and 3, so we got log of rho by rho naught is equal to minus of y by 1. So this one you will able to understand after learning the logarithm and integration. So just you try to understand this one here. And this one log of 0.46 divided by 1.25. So after simplification, we got this one as 8,000 meters. Or we can convert, if you convert in terms of kilometer, we got that one as balloon rises to a height of 8 kilometers. So that is the solution for B1. So got this one? Okay.